I'm Alex, and I'm the project manager of UWA Aerospace. We're a team 25 students strong from the University of Western Australia. And this is Kuka, our entry to the 10K category for the 2021 Spaceport America Cup. Kuka is the culmination of all practical skills and knowledge our team has developed over its 3 years of operation. Nearly every part of this rocket has been made in-house, ranging from the entire fuselage to both parachutes to a comprehensive parallel avionics system. A heavy focus has been placed on modularity, with the intention for key design features to be easily incorporated into and modified for future projects as our most senior members enter their last season with the team. By making this rocket as SRAD as possible, we're proud to give all our members such extensive practical application for their engineering degrees, as well as provide an opportunity for rocketry-based education that's fairly difficult to find in Western Australia. Kuka stands at 2.65 metres in height and has an outer diameter of 162 mil. Kuka is simulated to fly to 11,341 feet on a CTI M1290 motor, with our air brake system moderating this apogee to 10,000 feet. This same simulation predicts a maximum speed of 289 meters per second. Kuka features a dual brake, dual deploy recovery system. CO2 ejection mechanisms and redundant black powder charges ensure the ejection of a drogue parachute from the nose at apogee and a main chute from the aft at an altitude of 300 meters. Taking into account a dry mass of 14.7 kilograms, the drogue and the main achieve descent velocities of 23.6 and 7.46 meters per second respectively. A telemetrum flight computer and fully SRAD suite of PCBs are housed in the rocket's midsection. Both systems are capable of logging GPS and inertial data, as well as actuating the deployment mechanisms reliably and safely. 3 1U CubeSat payloads are situated in the nose of the rocket and contain adjustable ballast up to the weight of 5 kilograms each, or 15 kilograms in total.
The M1290 motor and accompanying Pro 98 3-grain 98mm casing weigh a total of 7.4 kilograms. This motor exerts a peak thrust of 1,500 newtons and has a burn time of 5.9 seconds. The motor and its casing slide into the motor tube from the bottom of the rocket and are secured by a retention plate. The rocket fuselage is split into 3 sections: the aft, the mid, and the nose. The nose, which holds the main parachute, is fixed to the midsection by shear pins, which keep the 2 sections joined until main deployment. The nose has an aluminium tip to protect against temperatures generated when the rocket reaches its near supersonic maximum speed. The midsection houses the Student Research and Develops Avionics PCB suite, our commercial off-the-shelf flight computer, and CO2 deployment mechanisms. 4 threaded rods span the section to dissipate parachute deployment forces, and all avionics are mounted onto our modular rack system, which utilizes these threaded rods as attachment points. Bulkheads are located at either end of the midsection. These feature venting holes for the CO2 deployment mechanisms and PVC tubes for housing black powder deployment charges. Additionally, inbuilt pyro terminals allow for quick attachment of E-matches and an electrical connection through to the midsection.
Through a combination of OpenRocket and SolidWorks, the launch of Kuka on our chosen motor gives a minimum stability of 1.45 cal and a thrust to weight of 5.94. Finite element analyses have shown that the engine block and bulkheads exhibit a minimum safety factor of 11.2 across all possible failure modes arising from parachute deployment forces and motor thrust. Hand calculations were carried out using the aeroelastic fin flutter equation to validate the rocket fin thickness and ensure it will not fail due to flutter.
All fiberglass and carbon fiber components inside the rocket are hand-laid by the team from fabric and resin. The main fuselage tubes are made by wrapping 6 layers of 200 grams per square meter twill weave fabric around the perimeter of a cylindrical mandrel. A single layer of pill ply is applied on the outer surface for smoothness, and the composites are left for 24 hours before being cured at 80 degrees Celsius for a further 4 hours. The fins are laid up with 12 layers of 250 grams per square meter carbon fiber fabric on a flat surface to create a single 5mm thick sheet. To make sure the fins are identical, a template is laser cut from the plywood and cut exactly onto the carbon fiber fins with a flush cut router.
Bulkheads, centering rings and mounting fixtures inside the rocket are made from plywood, an inexpensive and lightweight material whose alternating grain pattern offers superior strength and humidity stability compared to regular wood. The laser cutter allows us to manufacture these parts very quickly with a high level of precision. The laser can cut a thickness of up to 9mm, and thicker parts can be manufactured by stacking multiple layers and adhering them together with wood glue. Three-dimensional shapes are created from multiple flat pieces through interlocking box joints.
All centering rings and bulkheads are secured to the body tubes with 10-hour epoxy fillets. Construction is completed with the aid of comprehensive design plans. Having these plans completed before manufacturing has made the process significantly easier. The nose cone is laid up into an ABS mold. Because of its size, the mold is printed in several segments before being sanded and superglued together. The mold is then coated in 5 layers of PVA to assist in demolding. Next, pre-cut polygons of fiberglass are applied in layers to the 2 mold halves and adhered with epoxy resin. A lip is left on each half, which is used to join the mold together.
This rocket will be recovered with a dual brake, dual deploy deployment scheme. At apogee, the aft section of the rocket will separate from the midsection, releasing the drogue parachute. At 300 meters, the nose of the rocket will separate from the midsection to release the main parachute. A dual brake, dual deployment scheme was chosen over any single deployment scheme as it allowed for the inclusion of a drogue parachute that would greatly reduce the drift away from the launch pad with a fast initial descent. UWA Aerospace has also experimented with single brake dual deploy mechanisms, and these were found to be less reliable due to the risk of tangling. A dual brake mechanism ensures that all recovery components are kept within the body of the rocket until they're released.
The drogue parachute is a semi-ellipsoidal design with 10 gore panels and a spill hole that comprises 4% of the canopy volume. 10 suspension lines are attached to the canopy of this parachute. The main parachute is a parabolic design and the canopy is made of 6 panels. The design is inspired by Rocketman's high-altitude balloon parachutes. The main parachute has only 4 suspension lines, which simplifies packing and storage procedures and reduces the risk of tangling on inflation.
Both parachutes were manufactured in-house. The manufacturing of the drogue parachute involved the sewing together of the 10 gore panels with straight seams. Each seam allowance was finished with a zigzag stitch to prevent fraying. The spill hole and the skirt of the parachute were finished with bias binding, also to prevent fraying. As the main parachute consists of only 6 panels, a stronger seam was opted for. Each of the panels were joined with a felled seam.
A commercial, exhaustless Peregrine carbon dioxide recovery device is used to actuate parachute deployments. A 12-gram unit is used to eject the main parachute, and an 8-gram unit is used for the drogue parachute. Carbon dioxide deployment was chosen over traditional black powder charges to minimize the risk of explosive damage to rocket components. The Peregrine works by detonating a very small sealed black powder charge to push the carbon dioxide cylinder into a pin, causing the gas to vent through the bulkhead and separate the rocket. The functionality of the Peregrine device was tested successfully with both 8-gram and 12-gram CO2 cartridges. The parachutes were wind tunnel tested to confirm their inflation and stability. Both the main and the drogue parachutes were tested here in the University of Western Australia's wind tunnel at its maximum velocity of 7.7 meters per second. The test confirmed that both parachutes were able to fully inflate as expected with no observable parachute fluttering. Ground testing of primary and backup release mechanisms was also conducted. The CO2 system was able to separate the body tubes of the rocket and successfully eject the parachute. The redundant black powder charge was also successfully tested, and a charge size of 4.25 grams was found to be sufficient.
The avionics consists of 2 independent systems, one COTS and one SRAD. Our COTS altimeter is the Telemetrum from Altimetrum. This device was chosen because it has built-in GNSS tracking and a 433 MHz ISM transmitter to provide downlink. Additionally, it can detonate up to 2 E-matches, which is required to operate our dual deploy system. The team has also designed a suite of PCBs to monitor and control various rocket subsystems. Designed with modularity in mind, these boards fulfill basic functionality and provide a versatile foundation for future expansions and experimental subsystems. The first of our custom PCBs is the power management system. This board delivers power to all other modules in the avionics. It features a lithium-ion battery pack with built-in battery protection and USB-C charging. The output stage features a 5-volt buck boost converter and reverse power flow protection. The pack also includes custom switch circuitry, which ensures the system can only be deliberately powered on and off.
The heart of our SRAD system is the Altimeter PCB. This module includes a powerful microcontroller which reads sensors, performs flight calculations, and operates the dual deploy parachute system using our custom designed E-match ignition circuitry, which is optimized for reliability and safety. The functionality of the altimeter can be extended to include tracking by connecting it to our GNSS receiver module. This board includes a large patch antenna designed to maximize received signal power and maintain satellite lock.
To break out E-match connections, we have developed a feed-through PCB which is assembled onto the bulkhead. Terminal blocks either side of the bulkhead allow energetic devices to be connected inside or outside the avionics bay. Our system facilitates modularity with a few key features. The first is the ability to daisy-chain modules together through the power supply lines, which allows an arbitrary number of modules to be connected in parallel. Additionally, the altimeter also features a CAN bus, which provides an interface for it to control any future expansions to the system. All connectors in the system include mechanical latching mechanisms to ensure they cannot be disconnected by vibrations or high acceleration events experienced by the rocket.
The rocket payload consists of 3 1U stainless steel sheet metal containers of 1mm thickness. Each container features dividers that allow for partial filling while maintaining a mass distribution that is symmetric about the longitudinal axis of the rocket. The containers are held in a plywood fixture that is glued to the upper body tube and are sandwiched between layers of foam that dampen movement during flight.
KUKA has a student researched and developed air brake system, which adjusts the drag acting on the rocket through the actuation of flaps according to live data in order to decrease the apogee to exactly 10,000 feet. The air brake system is yet to be integrated into the full rocket, but as of current, in-depth CFD simulations have taken place, showing that the system is able to double the rocket drag coefficient. The rocket flight simulated on an open rocket with a drag coefficient profile that has been produced on RAS Aero. We use a combination of both software since OpenRocket has a more user-friendly interface, but RAS Aero is more accurate at predicting the drag coefficient for transonic flow regimes. Since trajectory simulations are carried out before the rocket's built, the mass of the rocket isn't known and we have to estimate it. An estimate of the entire fuselage mass and center of mass position is created from our virtual CAD assembly, which has the material density of every component inserted. A total dry mass of 14.7 kilograms was overridden in an open rocket, along with the center of mass position, and then we did a simulation on the M1290 motor. The rocket reaches a maximum speed of 289 meters per second and an apogee of 11,341 feet. This apogee is intentionally over the 10,000 feet so the air brakes can reduce it.
KUKA is expected to leave the launch rail 0.5 seconds after ignition. It hits max Q 5.4 seconds later, followed by burnout of the motor after an additional 0.2 seconds. The video you currently see on screen is a demonstration of our rocket's flight. After hitting max Q, the air brake system will power on. The system references its current speed and altitude to that generated by a simulation reaching 10,000 feet with the brakes half actuated. It then adjusts its speed through actuation of the brakes. At apogee, the primary ejection systems fire. This deploys the drogue parachute and the rocket begins its descent. At 300 meters, or around 1,000 feet, the secondary ejection systems fire, deploying the main parachute in preparation for landing. Whether it be the designing, building, or testing of KUKA, this rocket and this competition have been an extremely valuable experience for the team. Being able to get neck deep in rocketry once again after the pandemic-induced drought across 2020 has created a lot of motivation and excitement for our new members and reminded us older members why this field is so much fun. KUKA has allowed us to push further towards our goal of having an entirely SRAD rocket and also allowed us to test new ideas and refine existing ones. Through our modular design approach and detailed documentation, we believe that this rocket serves as an extremely versatile basis for future projects with future team members.